So, hello everyone. This is our project on blood glucose monitoring. So, this is done as a course project in the course CHN 302 Engineering Analysis and Process Modeling. So, the group members are Yash, Shubham, and Rishabh. So, this is our content of our slide. So, we will tell about the project, the objective of the project, then we will discuss the model assumptions, the parameter and equations. Then we will discuss and analyze our results. So, coming on to the introduction of our project, so why is blood glucose monitoring essential? So it is crucial for diabetes management as it involves continuous tracking of blood sugar levels. Also, it helps in real-time assessment of glucose dynamics so that we can take decisions according to it. So in this project, we have developed a mathematical model in which we have integrated two differential equations to simulate blood glucose dynamics. In this model, the equations which are used here accounts for accounts for the glucose production rate, insulin sensitivity, meal effect, exercise effects, and the lag time which is occurring due to the diffusion of blood glucose into the interstitial fluid. And later we have analyzed the results of this model, and finally the add-on of the project was to optimize the food intake and exercise duration when the blood glucose level were coming out of range. So the simulation software we used was MATLAB, in which we employed two differential equations, uh, and we solved the differential equation using ODE45. The first equation described a glucose kinetic, which in simple means it tells about how the glucose is being consumed or produced in the body due to the food intake or the insulin sensitivity or the exercise consumption. And the second was the equation to model the diffusion of glucose between the blood and the interstitial fluid. Basically, we are measuring the glucose level in the interstitial fluid as well. So coming on to the objectives of our project. So the first objective was to implement the model. So we developed a mathematical model for which included two differential equations for monitoring the blood glucose in the body. The second was the to simulate the glucose response due to the food intake or the exercise activities. As we consume the food, basically the glucose level would definitely rise up, and after some activities or exercise, the blood glucose level would go down. The third objective was to analyze the model output. Basically, we analyze the change of parameters or change of the daily habits of food intake or exercise or activities which change the blood glucose level in our body. And the final objective was to optimize the food intake and the exercise intensity when the blood glucose level were coming out of range. So basically, it told the model gave us result when the blood glucose was coming out of range. So coming on to the model assumptions, so we basically took some assumptions as basically we could not totally uh, compare the model with the real-time results. So we took some assumptions for some simplification. So we took constant rate of glucose production in our body. We took the constant rate for insulin sensitivity and glucose utilization rate. These all three parameters were assumed to be constant throughout the simulation. Also, the effect of meal, food intake, and the exercise or activities which we do are considered to be instantaneous and constant at that time step which the solver is solving. The third is that we have taken a constant lag time for the diffusion of the glucose in the blood to the interstitial fluid. Fourth assumption is that we have taken continuous glucose monitoring noise is assumed to be constant and taken to be have a standard deviation of 5 milligram per DL. The fifth assumption we have taken is that we have defined a safety threshold for the glucose level. The minimum for hypoglycemia is taken to be 70 and for hyperglycemia is taken to be 180 respectively. And the sixth assumption we have taken are the blood and interstitial fluid volumes, which and the body weight, which we have assumed for an average person to be 70 kilos, and correspondingly we have taken some assumption for blood volume and interstitial blood fluid volume. Now coming on to the model equations and parameters that we have used in this. So this is the first equation which is shown here. Del G by del T is taken is equal to glucose production rate minus insulin sensitivity into G plus meal effect into food intake at time step minus glucose intake rate utilization rate into G minus exercise effect into exercise intensity at time step T. This equation we have like thought of our on our own, like which we have considered two parameters of meal effect and the exercise effect. The meal effect would increase the blood glucose level, and the exercise effect would decrease the blood glucose level. And the glucose production rate has taken to be constant of 130 milligram per deciliter hour, and insulin sensitivity has also been taken constant to be around 0.6%, and meal effect and the exercise effect has also been taken constant of 20 and for 50 respectively. Now coming on to the second equation which we have modeled, like this equation tells us about the diffusion of the glucose from the blood to the interstitial fluid. So this equation is del G by del T is G of blood, which means blood glucose level, minus G, which is the interstitial blood glucose level, by lag time into blood volume by interstitial volume. And we have taken lag time to be around 5 to 15 minutes, and the blood volume is taken to be 4.9 liters, and the interstitial volume is taken to be 13.5 liters. All these are taken to be assumptions as discussed earlier, and these values might be changed to like in future to have better results.
So coming to our MATLAB code, here are the some defined constants and parameters which we have taken. So glucose production rate is 0.5 and insulin sensitivity is 0.1 and the following. These parameters are taken for a 70 kilogram human body, and the time frame we have taken here is of 6 hours. So we are first taking the input of food intake here and then taking the input of exercise intensity. Then there we have defined a function which is calculating the change in blood glucose levels cumulatively. Uh, then there is a function which is calculating the change in interstitial fluid glucose levels. This is also cumulatively calculating the glucose level which is diffusing through the interstitial fluid. There is a assumption that initial blood glucose level we have taken is 100 and the same for the interstitial glucose level. Then we have defined we are solving the differential equation using the OD45. After that we have determined that if the blood glucose level which is coming after the solving this differential equation is in the safe zone or not. And we have described the safe zone at safe low zone is 80, uh, safe low zone as 70 and safe high zone as 180. So the our result are coming in the safe zone or not, it is defining. After that we are plotting what the blood glucose levels are and what the interstitial fluid glucose levels are. And the third plot is for the food intake, where, the array we have taken as input, and the exercise intensity that take the array we have taken as input. Now for the optimization purpose, we have defined the optimization function here. So this is our function is score. After that, we have set the bounds of the optimization, that food bound should be the 0 to 100 and exercise bound should be 0 to 3. We have used a genetic algorithm for the optimization purpose here, GA. Here comes optimal array of food intake and optimal array of exercise intensity, which should be we have to taken if to lie the glucose level and interstitial fluid glucose level in the safe range. After that, we are plotting the glucose level and the fluid glucose level, interstitial fluid glucose level, so that it comes in the safer range. Thank you.
Now coming back to the presentation, so we have shown this result without optimization. So this results are for the value uh, which are for a normal input without optimization. So we can see here that during some part of the day, the blood glucose levels are coming out of the safe range of 70 to 180. So after optimization, we have found out that the So after optimization, we can see here that our code tell us the optimized results of the food intake and the exercise effect, so that the blood glucose levels in the interstitial fluid lies in the safe range. So thank you. This was all for our presentation.